For number one, you're told to assume x and y are both differentiable functions of t. Find dx dt given x equals -1 and dy dt equals 8. So the first thing we have to do is find the derivative of our given equation. So that's going to be 8x dx dt plus 9y squared dy dt equals 0. And then notice that you're told that x is -1 and dy dt is 8. So let's go ahead and plug in what we know. So we have 8 times -1. We're looking for dx dt plus 9, and then y. Were we given a y value? We were not. So we have y squared. We'll have to go find that value. But we were told dy dt is 8. And all of this equals 0. So in order to find what our y value is, we're going to have to plug in -1 for x. So over to the side, we're going to substitute in that -1, and we're going to have 4 times -1 squared plus 3y squared equals 28. So we're going to have 3y squared equals 24. And so let's see, dividing by, that's 3y cubed. So here, dividing 3 by 3, we have y cubed equals 8. So that means that y has to be 2. So now back over to our problem itself, we are going to have -8 dx dt plus, and we're going to have 9 times 2 squared, so 4, times 8 equals 0. And now it's just a matter of solving the rest of this, and you should get dx dt to be 36. For number 2, we're told that water is falling on a surface, wetting the circular area. That is expanding at a rate of 10 millimeters squared per second. How fast is the radius of the area expanding when the radius is 116 millimeters? So what we need to do is find the area of a circle. So that's something they're assuming we should know. Area is pi r squared, and when we find the derivative with respect to time, notice that we end up with something we can do some substitutions with. Now, going and substituting in what we know that the rate of the circular area, so we're going to have 10, and we can include our units here or wait to the end, so whichever you want to do. It's going to be equal to 2 pi times our radius squared. And what's going to be our 2 pi r? Our radius was 116. And let's see, we are looking for how fast the radius of the area is expanding. So we're looking for dr dt. And so we're going to divide both sides by 2 pi times 116. So I have 10. Let's bring down our units. Over, and we have 2 pi, and then 116. And I wouldn't do just a whole lot of simplifying here. Of course, you could cancel the 2 and the 10. But as far as writing all of this out, I wouldn't. So you're going to have 5 over 116 pi, and that is fine. Leave it like that. All right, so hopefully we got through number 2. Number 3, we have a spherical ball that's being inflated. The radius of the balloon is increasing at a rate of, so there's your dr dt. We've got 1 over pi inches per second. find the rate at which the volume is increasing. So we're looking for dV dt when the radius is 1 inch. So our volume formula here, and this is something you would be given on the exam, you have 4/3 pi r cubed. And let's go ahead and find the derivative because we know we're going to have to anyway. So we have 4 pi r squared dr dt. Now we're looking for volume, the change in the volume, so we know dV dt equals, and we have 4 pi. We need to know what the radius is, and it says 1 inch. So we're going to have 1 squared and times the rate of change of the radius, which was 1/pi inches per second. So our volume, dV dt, the rate of change of the volume, looks like it's going to end up being 4. And if you go back and check your units, it should be inches cubed per second. Alright, so for our next one, we're talking about the edges of a cube, and they are expanding. And so we need to talk about the volume. So the volume here is just going to be side cubed since we're talking about a cube. So let's go ahead and take the derivative of our volume formula. And so we're going to have 3s squared ds dt. And now we're ready to substitute in. Now we're wanting to see how fast the volume is changing, so that's dV dt equals, and we have 3 times, and notice the edges are expanding, so that's going to be our ds dt, and the edge is going to be 10 centimeters here. So our side squared times our rate of change of the side, which was 3. So it looks like our volume is changing at a rate of 900 centimeters cubed per second. Number 5, an aircraft is climbing at a 30-degree angle to the horizontal. How fast is the aircraft gaining altitude if the speed is 500 miles per hour? So we need to draw a triangle. And if the aircraft is climbing at a 30-degree angle, so that means we've got something like this. Okay, so this angle inside here is 30 degrees. And here is going to be how far the plane is traveling, and there's going to be the altitude. And so really we can use our sine formula. We know sine of 30 degrees is going to be y over d. We can move our d over to the other side, so we have d times sine of 30 equals y. And we know that sine of 30 is 1/2, so really we have 1/2 d, change the letter, it's got to be capitalized, equals y. So then that tells me that I know 1/2, well, let's see, that's going to be d over dt equals 1 dy dt. And so we're about finished because we want to know how fast is the aircraft gaining altitude. So this part right here is what we're looking for, is that rate of change. And we know that it's changing here, the speed, that rate of change there is 500 miles per hour. So we're going to have 1/2 times 500, and that's going to be the rate of change of the altitude. So it looks like it's changing altitude by 250 miles per hour. Okay, a 6-foot-tall man walks at a rate of 5 feet per second away from a lamppost that is 22 feet high. So, sounds like a good right triangle problem. So we have a lamppost that is 22 feet high, and the 6-foot-tall man is walking away from the lamppost. So our man should be somewhere right in this area here. And we know he is 6 foot tall. At what rate is the length of his shadow changing when he is 60 feet away from the lamppost? So we've got two areas here that we're looking at, X and Y. And we really can set up a proportion here. So we know that, let's see, 6 and 22 are related. So 6 and 22 is equal to, well, that's going to be y, x plus y, this whole base of the triangle, over just this portion that's associated with the side of 6, which is y. So if we cross multiply, we have 22y equals 6x plus 6y. And so we have 16y equals 6x. And so solving for y, just because that's what we normally do, we have 6 over 16x. And I would reduce that because we are about to take the derivative of it. So that means that y equals, if we reduce that, that's going to be 3 over 8 x. Now let's talk about the rate of change of those, because both sides are changing. So if we do our derivative, so we're going to have dy dt equals 3 over 8 dx dt. And so notice that the man walks at a rate of 5 feet per second away from the lamp. So that's going to be, back over here, he is walking away from the lamp. So that's the rate of change for x. So back over, we can make the substitution, dy dt equals 3 over 8 times, and he was walking at 5 feet per second. So notice that the rate of change of y is going to be 15 over 8, and it's going to be feet per second. All right, number 7, glancing through the problem, you're talking about a cylinder. So we need the volume formula for a cylinder, which is pi r squared h. And something to note here with the cylinder, let's see. So it wants to know that the radius is 4 centimeters, is increasing at a rate of 2 centimeters per minute. So find the rate at which the volume with respect to time is changing when the height is 10 centimeters. So what we have is a cylinder. And notice with the cylinder that if we're filling the cylinder up, that the height is definitely changing, but the radius here is staying the same. The radius doesn't change here, but definitely the height does, because you're talking about as this fills up with whatever. So when we go through, before we do anything, since we're told that the radius is 4, keep in mind that is constant. The radius is not changing. So we can go ahead and sub that in. And so we see that the volume is going to be 4 squared. So 16 pi h. And that's going to make that a little bit easier to work with, because now when we do our derivative, so we have dv over dt equals 16 pi dh dt. And we are told that the height, let's see, find the rate of change of the volume with respect to time when the height is 10 centimeters. So we've got enough information now to go through and figure out. So at 2, so we're going to go sub in our 2, because here again we're told that the height, the radius of 4 is increasing at 2. So there's our rate of change for our height. So dv dt is going to be 16 pi times 2. So that's going to give us 32 pi, and our units would be centimeters cubed per minute. A conical water tank is 24 feet high and has a radius of 10 feet at the top. So now earlier when we talked about the radius of a cylinder, that radius was constant. This is not going to be constant because we have that conical shape. So really I have something, let's see, and it doesn't say it was inverted, but let's see, if we had our cone, it's going to have something like this. So it is changing, and notice here it tells us that our height, the conical water tower, has a height of 24 feet. So we have our height here, and it has a radius of 10 feet at the top. So now note that that radius is not constant. It's going to change through the cone. But here the radius is 10 feet at the top. So if water flows into the tank at a rate of 20 cubic feet per minute, how fast is the depth of the water? So we need the volume of a cone, which is going to be 1/3 pi r squared h. Now, if we do our derivative here, we've got to have the product rule, and we really don't want to do that. We are looking for how fast is the depth of the water increasing. So we're looking for a height, or no, we're looking for the volume. How fast is the depth of the water? So we're looking for a volume. So over here, we know that the relationship of R to H is going to be 10 to 24. And that can reduce down to be 5 to 12. And so we have a relationship with these, and we could say, well, R is really equal to 5 over 12 times H. If I wanted to move H over here, I would multiply it. And so if we make that substitution in our volume, that's going to make this a little easier to work with because we're eliminating one of these variables. So we have 1/3 pi, and R, we're going to make that 5 over 12 H, and that's squared, times H. So let's see what that ends up giving us. Now I know we're doing a lot of math here, but it's going to save us some steps whenever we do our derivative. So we are going to have the volume equals, let's see, we're going to have 1/3 pi. 5 squared is 25, so we're going to have 25 over 144. And then our H, let's see, that's going to be H to the third. Now we're down to one variable. Now let's see what happens when we take the derivative. So we're going to have dv over dt equals, well, that 3 is going to multiply down to the front. Yay, that's what we were hoping to happen. So we're going to have pi times 25 over 144 h squared dh dt. All right, and so now we need a rate of change for the height. And let's see what it tells us. It tells us that how fast is the depth of the water increasing when the water is 16 feet deep. So we can go ahead then and find our H was 16, so we need to go ahead and plug in there. So we have dv dt equals pi times 25 over 144 times 16 squared dh dt, and we're running out of room there. All right, so now we've got to find dh dt. So we see that the water is flowing into the tank at 20 cubic feet per minute. So that's going to be our rate of change of our volume. So we have 20 equals, we have pi times 25 over 144 times 16, and here's our dH/dt that we've got to find. So we're going to divide all this over, I think that's 16 squared. Yep. So we're going to have 20 divided by, we have pi, and let's see, we have 16 squared, so I'm going to just rewrite this out because I don't have a calculator. And let's see, I think that's also going to put 25 down here, but 144 is going to go up in the numerator. So that's going to be equal to dH dt, and now we're going to just do some canceling here. Let's see, 25 and 20, I'm going to both take out a 5. 16 cancels into 144, leaving 9. And 4 cancels into 16, leaving a 4. So it looks like that we end up with 9 over 20 pi is the rate of change of our height.